For a shaft with a wall thickness much smaller compared to its radius, the variation in shear stress and moment arm become very small through the wall thickness. It is thus convenient to approximate this stress state as constant through the wall thickness. To help remember that we are making this simplification, it is convenient to multiply the stress by the wall thickness, resulting in a shear force per unit length around the perimeter of the shaft. This quantity represents the flow of the shear force around the cross-section and is thus referred to as the shear flow. For the thin-walled circular shaft shown here, it is clear due to the constant radius and shaft wall thickness that the shear flow will remain constant. But what if this cross-section is not circular? And what if the thickness around the perimeter is variable? To generalize our analysis, we will consider an arbitrary thin-walled shaft with a closed cross-section subjected to torsion. We will allow the thickness to vary around the cross-section. However, the thickness at every location must be much smaller than the distance of the cross-section perimeter to the central axis of the shaft. To illustrate these constraints, consider the following three cross-sections. The first section clearly meets all of these constraints. However, in the rectangular section, the wall thickness is not sufficiently small compared to the overall width of the cross-section, and thus would not be suitable for this analysis. Finally, the last cross-section is also not suitable as it is an open section rather than a closed section. Let's use the first section to illustrate our generalized shaft. If we take a closer look at our generalized shaft, we can analyze a rectangular element passing through the entire thickness of the shaft wall. In this shaft, the thickness can vary along the perimeter, but it is constant along the length of the shaft due to the constant cross-section. If we zoom in on this element and examine the shear flow distribution, we can see that along BC, we will allow the shear flow to vary from QB at point B to QC at point C. As the cross-section of the shaft is constant, the thickness along length AB is constant and equal to the thickness at B. Combined with the principle of complementary shear stress, this means that the shear flow along length AB and the shear flow at A along AD are both equal to QB. Repeating the same for the bottom half of the element, we obtain that the shear flow along length DC is equal to QC. With the shear flows defined, we can now enforce equilibrium along the length of the shaft. Looking at the forces acting in the direction of the axis of the shaft, we find that the resultant shear force, QB times dx, along length AB is equal to the resultant shear force, QC times dx, along length DC. Simplifying, we find that QB must equal QC, and thus the shear flow is constant around the perimeter of the section. We will relate resultant torque to the shear flow distribution in an arbitrary thin-walled closed-section shaft. In the drawing showing here, the wall thickness has been exaggerated so that we can more clearly annotate it during our derivation. However, it is important that the conditions for a thin-walled shaft discussed in the previous video still apply. If torsion is being transmitted by this shaft, there will be an internal torque which we will label T acting on the cross-section. This torque is a resultant of the shear flow acting along the perimeter of the cross-section. To relate these, let's consider an infinitesimal element of the shaft perimeter with a length ds. The shear flow acting on this element will produce a resultant force which we will call df. Because the element is infinitesimal, the curvature of the path ds is negligible, and the resultant force is precisely equal to the shear flow Q multiplied by the element length ds. This resultant shear force will generate a moment dt that contributes to the overall resultant torque of the cross-section. To define this moment, we will define a datum point, O, about which to sum all of the torsional moments acting on the cross-section. Denoting the moment arm for df about point O as r, we can express the moment due to df as dt equals r times df. Substituting in our result for df, we get that dt is equal to r times q times ds. If we integrate this result over the entire perimeter of the cross-section, we can obtain the total resultant torque T. If we recall from previous video, shear flow is constant in the case of torsion and thus can be removed from the integral, resulting in the following integral equation. What does this integral represent physically? Well, r times ds defines a rectangular area. If we look at our section closely, we see that r sweeps out a triangular area along ds. This triangular area is precisely 1/2 the rectangular area r times ds. Recognizing that the area swept by r around the entire perimeter is equal to the area enclosed by the median line, we can see that the integral of r times ds must be equal to twice the area enclosed by the median line. Taking this result, we can forget about needing to solve integrals and simply replace the integral with twice the enclosed area. Typically, we are interested in determining the shear flow from the resultant torque, so the equation can be rearranged as follows. This analog to the torsion formula for thin-walled closed sections is commonly referred to as Bredt's formula.